This presentation is delivered by the Stanford Center for Professional Development.
Good afternoon. All right, you guys are talkative. So just we talked just a little bit about the vocabulary of recursion at the end of Friday, and it was very rushed for time. So I'm just going to repeat some of those words to get us thinking about what the context for solving problems recursively looks like, and then we're going to go on and do a lot of examples. So the idea is that a recursive function is one that calls itself. That's really all it means, right? At the most trivial level, it says that in the context of writing a function Binky, it's going to make a call or one or more calls to Binky itself, passing an argument as part of solving or doing some task. The idea is that we're using that because the problem itself has some self-similarity, where the answer I was seeking, so the idea of surveying the whole campus, can actually be thought of as, well, if I could get somebody to survey this part of campus and this part of campus, somebody to survey all the freshmen, somebody to and whatnot, that those in a sense are, those surveys are just smaller instances of the same kind of problem I was originally trying to solve, that if I could recursively delegate those things out, and then they themselves may in turn delegate even further to smaller but same structured problems, to where we could eventually get to something so simple, in that case of like, well, asking 10 people for their input, that don't require any further decomposition. We will have worked our way to this base case that then we can gather back up those results and solve the whole thing. This is going to feel very mysterious at first. And some of the examples I give, you'll say, well, I have really easy alternatives other than recursion, so it's not going to seem even worth the pain of trying to get your head around it. But eventually we're going to work our way up to problems where recursion really is the right solution, and there are no other alternatives that are obvious or simple to do. So the idea throughout this week is actually just a lot of practice. That telling you what the terms mean, I think, is not actually going to help you understand it. I think what you need to see is examples. And so I'm going to be doing 4 or 5 examples today, 4 or 5 examples on Wednesday, and 4 or 5 examples on Friday, that each kind of build on each other, kind of take the ideas and get a little more sophisticated. But by the end of the week, I'm hoping that you're going to start to see these patterns and realize that in some sense, that recursive solutions tend to be more alike than different. That once you have your head around how to solve one type of problem, you may very well be able to take the exact same technique and solve several other problems that may sound different at first glance, but in the end, the recursive structure looks the same. So I'd say just hold the discomfort a little bit and wait to see as we keep working which example may be the one that kind of sticks out for you to help you get it through. So we're going to start with things that fit in the category of functional recursion. The functional in this case just says that you're writing functions that return some non-void thing, an integer, a string, and some vector of results or whatever that is. And that's all it means to be a functional recursion. It's a recursive function that has a result to it. And because of the recursive nature, it's going to say that the outer problem's result, the answer to the larger problem, is going to be based on making calls, one or more calls, to the function itself to get the answer to a smaller problem, and then adding them, multiplying them, comparing them to decide how to formulate the larger answer. All recursive code follows the same decomposition into 2 cases. Sometimes there's some subdivisions within there, but 2 general cases. The first being this base case. That's something that the recursion eventually has to stop, right? That we keep saying, take the task and break it down, make it a little smaller. But at some point, right, we really have to stop doing that, right? We can't go on infinitely. There has to be some base case, the simplest possible version of the problem that you can directly solve. You don't need to make any further recursive calls. So the idea is that it kind of bottoms out there and then allows the recursion to unwind. The recursive cases, and there may be one or more of these, right? In the case where it's not that simple, that the answer isn't directly solvable, but if you had the answer to a smaller, simpler version, you would be able to assemble that answer you're looking for using that information from the recursive call. So that's the kind of structure that they'll all look like. Some sort of test. If I'm at the base case, then do the base case thing and return it. Otherwise, make some recursive calls and use that to return a result from this iteration. So let's first look at something that the first couple examples I'm going to show you actually are going to be so easy that in some sense they're almost going to be a little bit counterproductive, because they're going to teach you that, well, recursion doesn't let you do things you already know how to do. And then I'm going to work my way up to ones that actually get beyond that. But let's look at first the raised to power. C++ has no built-in exponentiation operator. There's nothing that raises a base to a particular exponent in the operator set. So if you want it, you need to write it, or you can use, there's a math library called POW for raised to power. We're going to write our own version of it because that's going to give us some practice thinking about this. And the first one I'm going to show you is one that should feel very familiar and very intuitive, right, which is using an iterative formulation. If I'm trying to raise base to the exponent, then that's really simply multiplying base by itself exponent times. So this one uses a for loop and does so, right? Starts the result at 1, and for iterations through the number of exponents, right, keeps multiplying, right, to get there. Now, so that one's fine, and it will perfectly work. I'm going to show you this alternative way that starts you thinking about what it means to divide a problem up in a recursive strategy. Base to the exponent. I want to raise, 5 to the 10th power. If I had around some delegate, right, some clone of myself that I could dispatch to solve the slightly smaller problem of computing 5 to the 9th power, then all I would need to do is take that answer and multiply it by one more 5, and I get 5 to the 10th. Okay. If I write code that's based on that, then I end up with something here, and I'm going to let these two things go through to show us that to compute the answer to 5 to the 10th power, what I really need is the answer to 5 to the 9th power, which I do by making a recursive call to the same function I'm in the middle of writing. So this is raise that I'm defining, and in the body of it, it makes a call to raise. That's what is the mark of a recursive function here. I pass slightly different arguments. In this case, write one smaller exponent, which is getting a little bit closer to that simplest possible case, right, that we will eventually terminate at, where we can say, well, I don't need to further dispatch any delegates and any clones out there to do the work. That if the exponent I'm raising it to is 0, by definition, anything raised to the exponent of 0 is 1, I can just stop there. So when computing 5 to the 10th, right, we're going to see some recursion at work. Let me take this code into the compiler. So that we can see a little bit about how this actually works in terms of that. So that's exactly the code I have there. And I can say, something that I know the answer to. How about that? First, we'll take a look at it. Doing its work, so 5 times 5 times 5 should be 125. So we can test a couple little values while we're at it, right? 2 to the 6th power, that should be 64. Just to see a couple of the cases, just feel good about what's going on. And then raising, let's say, 23 to the 0 power should be 1, as anything raised to the 0 power should be. So a little bit of spot testing to feel good about what's going on. Now, I'm going to go back to this idea of like 2 to the 6th. And I'm going to set a breakpoint here. Take that breakpoint out. And I'm going to run this guy in the debugger. Takes a little bit longer to get the debugger up and running, so I'll have to make a little patter up while we're going here. And then it tells me right now it's breaking on raise, and I can look around in the debugger, and this is a, look at that. Did it not pick up my compilation? I think it did not. I must not have saved it right before I did it, because it's actually got the base is 23 and the exponent is 0. Turns out I don't want to see that case, so I'm going to go back and try again. I want to see it. Okay. Oh, oops. Oh, I did not. The debugger. Okay. And I'm just interested in knowing a little bit about the mechanics of what's going to happen in a recursive situation. That if I look at the first time I hit my breakpoint, then I'll see that there's a little bit of the, the beginnings of the student main, some stuff behind it. There's a little bit of magic underneath your stack that you don't really need to know about. But starting from main, it went into raise, and the arguments it has there is the base is 2, the exponent is 6. If I continue from here, then you'll notice the stack frame got one deeper. There's actually another invocation of raise, and in fact, they're both active at the same time. That the previous raise that was trying to compute 2 to the 6th is kind of in stasis back there, waiting for the answer to come back from this version, right, which is looking to raise 2 to the 5th power. If I continue again, I get 2 to the 4th. I keep doing this, right? I'm going to see these guys kind of stack up, each one of those kind of waiting for the delegate or the clone to come back with that answer so that then it can do its further work incorporating that result to compute the thing it needed to do. I get down here to raising 2 to the 1st power, and then finally I get to the 2 to the 0, and so now I've got these 8 or so stack frames, six up there. This one, if I step from here, right, it's going to hit the base case of returning 1, and then we will end up kind of working our way back out. So now we are at the end of the 2 to the 1 case, right, that's using the answer it got from the other one, multiplying it by 2. Now I'm at the 2 to the 2 case, and so each of them is kind of unfolding, and the stack is what's called unwinding. It's popping back off the stack frames that are there and kind of revisiting them, each passing up the information it got back, and eventually, telling us that the answer was 64. So I will let that go. Okay. So the idea that all of those stack frames kind of exist at the same time, right? They're all being maintained independently. So the idea that the compiler isn't confused by the idea that raise is invoking raise, which is invoking raise, that each of the raise stack frames is distinct from the other ones. So the invocations are actually kept separated. So one had 2 to the 6th, the next one had 2 to the 5th, and so on. And then eventually we need to make progress toward that base case so that we can then stop that recursion and unwind. Let me actually show you something while I'm here, which is that one thing that's a pretty common mistake to make early on in a recursion is to somehow fail to make progress toward that base case, or to not all cases make it to the base case. For example, if I did something here where I forgot to subtract 1 up it, and I said, oh yeah, I need to raise, in this case I'm passing it exactly the same arguments I got. If I do this and I run this guy, then what's going to happen is it's going to go to the 6, to the 6, to the 6, right? And I'm going to let go of this breakpoint here because I don't really want to watch it all happening. And there it goes. Loading 6,493 stack frames, 0% completed. It's going to take a while, as you can imagine. And usually once you see this error message, it's your clue to say, yeah, I can cancel. I know what happened, right? The only reason, right, I should have gotten, 6,500 stack frames, right, loaded up is because I made a mistake, right, that's caused the stack to totally overflow. And so the behavior, right, in C++ or C, right, is that when you have so many of those stack frames, eventually the space that's been allocated or set aside for the function stack will be exhausted. It will use all the space it has and run up against a boundary, and typically report it in some way that suggests, sometimes you'll see stack overflow, stack out of memory error, in this case showing you the 7,000 stack frames, right, that are behind you, and then if you were to examine them you could see, oh, they all have exactly the same arguments and they weren't getting anywhere. I'm not going to actually let it do that because I'm too impatient. Let me fix this code while I'm here. But other things, right, that even this code that actually looks correct for some situations also has a subtle bug in it. Even after I fix this, right, which is that right now it assumes that the exponent is positive, right, that it's some number that I can subtract my way down to 0. If I actually miscalled raise and I gave it a negative exponent, right, it would go into infinite recursion as well, right? If you started it at 10 to the negative 1st power, right, it would go negative 1st, negative 2nd, negative 3rd, 6,500 stack frames later, right, we'd run out of space. In the case of this, right, since we're only intending to handle those positive powers, we could just put an error in there. There's like, yeah, if the exponent is less than 0, then raise an error and don't even try to do anything with it. Okay. So let me show you just a slightly different way of doing this that's also recursive, but that actually gets the answer a little bit more efficiently. And this is a different way of dividing it up, but still using a recursive strategy, which is that if I'm trying to compute 5 to the 10th power, that if I had the answer not of 5 to the 9th power, but instead I had the answer of 5 to the 5th power, and then I multiplied that by itself, I would get that 5 to the 10th power that I seek. And then there's a little bit of the case, though, of like, well, what if the power I was trying to get was odd? If I were trying to raise it to the 11th power, right, I could compute the half power, right, which get me to the 5th multiplied by the 5th, but then I need one more base multiplied in there to make up for that half. Okay, and so I can write another recursive formulation here. Same sort of base case, right, about detecting when we've gotten down. But then in this case, the recursive call we make is to base of the exponent divided by 2. And then we use it with the if-else on whether the exponent was even or odd to decide whether to just square that number or to square it and tack in another power of the base while we're at it. So this one, right, is going to be much more quick about getting down to it, whereas the one we saw, right, was going to put one stack frame down for every successive exponent power. So if you wanted to raise something to the 10th or 20th or 30th power, right, then you were giving yourself 10, 20, 30 stack frames. Something like, 30 stack frames is not really something to be worried about, but if you were really trying to make this work on much, much larger numbers, which would require some other work because exponent is a very rapidly growing operator to overflow your integer quickly. But this way, right, very quickly divides in half. So it goes from a power of 100 to a power of 50 to 25 to 12, to 6 to 3 to 2 to 1. So that dividing in half is a much quicker way to work our way down to that base case and get our answer back. And we're doing a lot fewer calculations than all those multiplies, one per base. So just a little diversion. So I want to tell you something that just a little bit about kind of style as it applies to recursion. That recursion is really best when you can express it in the most kind of direct and clear and simple code. It's hard enough to get your head around a recursive formulation without complicating it by kind of having a bunch of extraneous parts, right, where you're doing more work than necessary or redundantly handling certain things. And one thing that's actually very easy to fall in the trap of is thinking about, well, there's lots of other base cases you might be able to easily handle, so why not just go ahead and call out for them, test for, you're at the base case, you're close to the base case, checking before you might make a recursive call. If you're going to hit the base case when you make that call, well, then why make the call? I'll just anticipate it and get the answer it would have returned anyway. And it can lead to code that looks a little bit like this before you're done. You're like, oh, well, if the exponent is 0, that's 1. Well, if it's, the exponent is 1, well, I can just return the base. Well, if it's 2, I can just multiply base by itself. And if it's 3, I can start doing this. Certainly you can follow this to the point of absurdity. And even for some simple cases, it might seem like, well, you're saving yourself a little bit of extra time. You're like, well, why go back around and let it make another recursive call, right? I can stop it right here. It's easy to know that answer. But as you do this, right, it complicates the code, right? It's a little harder to read. It's a little harder to debug. And really, the expense of making that one extra call, 2 extra calls, is not the thing to be worried about. What we really want is the cleanest code, right, that expresses what we do, that has the simplest cases to test and to examine and to follow, and not muck it up with things that, in effect, right, don't change the computational power of this, but just introduce the opportunity for error. Like instead of a multiply here, I accidentally put a plus, right? It might be easy to overlook it, right, and not realize what I've done. And then end up, computing the wrong answer based on when it gets to the base case of 2. In fact, if you do it this way, right, it's like most things would stop at 3, but then these would suddenly become kind of their own special cases that were only hit if you directly called them with a 2. The recursive cases will all stop earlier. It complicates your testing paths now because not everything is going through the same code. So we call this arm's length recursion. I put a big X on that. Looking ahead, testing before you get there. Just let the code fall through. So Dan, who's not here today, but he talked to me at the end of Friday's class, and it made me want to actually just give you a little bit of a insight into recursion as it relates to efficiency. That recursion by itself, just the idea of applying a recursive technique to solving a problem, does not give you any guarantee if it's going to be the best solution, the most efficient solution, or the fact that it's going to give you a very inefficient solution. I think sometimes people have kind of a bad rap on recursion. It's like, oh, well, recursion will definitely be inefficient. That actually is not guaranteed. Recursion often requires exactly the same resources as the iterative approach, that it takes the same amount of effort, right? Surveying the campus. If you're going to survey the 10,000 people on campus and get everybody's information back, whether you're doing a divide and conquer, or whether you're sitting out there in White Plaza asking each person one by one, in the end, 10,000 people got surveyed. that the recursion is not part of what made that longer or shorter. It might actually, depending on kind of how you have resources, work out better. Like you could get a bunch of people in parallel surveying. You might end up completing the whole thing in less time, but it required kind of more people and more clipboards and more paper while the process was ongoing than me standing there with one piece of paper and a clipboard. But then again, it took lots of my time, right, to do it. So in many situations, it's really no better or no worse than the alternative. It makes a little bit of some trade-offs of where the time is spent. There are situations, though, where recursion can actually make something that was efficient inefficient. There are situations where it can take something that was inefficient and make it efficient. So it's more of a case-by-case basis, right, to decide whether recursion is the right tool if efficiency is one of your primary concerns. I will say that for problems with simple iterative solutions that, that operate relatively efficiently, iteration is probably the best way to solve it. So raised to power, it's like, yeah, you can certainly do that iteratively. There's not some huge advantage that recursion is offering. I'm using them here because they're simple enough to get our head around. We're going to work our way toward problems where we're going to find things that require recursion, which is kind of one of the third points I put in. Well, then why do we learn recursion? What's recursion going to be good for? First off, recursion is awesome. There are some problems, right, that you just can't solve using anything but recursion. So that the alternative is like, well, I'll just write it iteratively, won't work. Right, you'll try, but you'll fail. Right, that they inherently have a recursive structure to them where recursion is the right tool for the job. Often it produces the most beautiful, direct, and clear, elegant code. The next assignment that will go out has these problems that you do in recursion, and they're each about 10 lines long. Some of them 5 lines long. They do incredible things in 5 lines because of the descriptive power of describing it as here's a base case and here's a recursive case, and everything else just follows from applying this and reducing the problem step by step. So you will see things that where the recursive code is just beautiful, clean, elegant, easy to understand, easy to follow, easy to test, solves a recursive problem. And in those cases, it really is a much better answer than trying to hack up some other iterative form that may in the end be just no more efficient and maybe even less efficient. So don't let efficiency be kind of a big fear of what recursion is for you. Okay. So I'm going to do more examples. I got like 3 more examples, so or 4 I think today. So I will just keep showing you different things, and hopefully the patterns will start to kind of come out of the mist for you. A palindrome string is one that reads the same forwards and backwards when reversed, right? So was it a car or a cat I saw, right? If you read that backwards, it turns out it says the same thing. Go hang a salami, I'm a lasagna hog. Also, right? Handy when you need to have like a bar bet over what the longest palindrome is to have these things around. There's certainly ways to do this iteratively if you were given a string and you're interested to know, well, is it a palindrome? That you could kind of do this marching where you're looking outside and kind of marching your way into the middle. But we're going to go ahead and let recursion kind of help us deal with the sub-problem of this and imagine that at the simplest possible form, right, you can say, well, a palindrome consists of an interior palindrome and then the same letter tacked onto the front and the back. So if you look at was it a car or a cat I saw, there are 2 W's there. It starts and it ends with a W. So all palindromes must start and end with the same letter. Okay, let's check that. And if that matches, then extract that middle and see if it's a palindrome. Okay, so it feels like I didn't really do anything, right? It's like all I did was match 2 letters, and then I said, okay, and then by the way, delegate this problem back to myself, making a call to a function I haven't even finished writing to examine the rest of the letters. Okay, and then I need a base case. I got a recursive case, right? Take off the outer 2 letters, make sure they match, recur on the inside. What is the simplest possible palindrome?
1 letter.
1 letter. 1 letter makes a good palindrome, right? 1 letter, right, is like by definition, right? First and last letter are the same letter, so it matches. That's a great base case. Is it the only base case? 2 letters, yeah. 2 letters is also kind of important, but like there's actually an even simpler form, right?
Empty string.
It's the empty string, right? So both the empty string and a single character string are by definition, right, the world's simplest palindromes, right? They meet the requirements, right, that they read the same forward and backwards. Empty string forwards and backwards is trivially the same. And so that makes it even easier than doing the 2-letter case. So if I write this code to look like that, where if the length of the string is 1 or fewer, so that handles both the 0 and the 1 case, then I return true. Right? Those are trivial palindromes, right, of the easiest, immediate detection. Otherwise, right, I've got a return here that says, if the first character is the same as the last character, and the middle, so the substring starting at position 1, that goes for length minus 2 characters, that picks out the interior, discarding the first and the last characters. If that's also a palindrome, then we've got a palindrome. And so given the short-circuiting nature of the and, if it looks at the outer 2 characters and they don't match, it immediately just stops right there and says false. If they do match, then it goes on looking, at the next interior pair, which will stack up a recursive call looking at its 2 things. And eventually we will either catch a pair that doesn't match, and then this false will immediately kind of return its way out, or we'll keep going all the way down to that base case, hit a true, and know that we do have a full palindrome there. So you could certainly write this with a for loop. It's actually, writing it with a for loop is, I think, almost a little bit trickier because you have to keep track of kind of, well, which part of the string are you on and what happens when you get to the middle and things like that. That in some sense that the recursive form really kind of sidesteps that by really thinking about it in a more holistic way of like, well, the outer letters plus an inner palindrome gives me the answer I'm looking for. So this idea of taking a function you're in the middle of writing and making a call to it as though it worked is something they require this idea of the leap of faith. Like you haven't even finished describing how is palindrome operates, and there you are making a call to it, depending on it working in order to get your function working is a very kind of wacky thing to get your head around. It feels a little bit mystical at first. So that feeling that you feel a little bit sort of discombobulated about this is probably pretty normal. But we're going to keep seeing examples and hope that it starts to feel a little less unsettling. Anybody want to ask a question about this so far? Yeah.
So I guess create your base case first and then test it.
So that's a great question. So I would say typically that's a great strategy, right, is get a base case and test against the base case. Sit in the 1 character, the 2 character strings, and then imagine kind of one layer out, things that will make one recursive call only, right? And so in this case for the palindromes, it's like, well, what's a 2 character string, right? One that has AB, one that has AA, right? So one that is a palindrome, one that isn't, and watch it go through. Then from there you have to almost take that leap and say, it worked for the base case, it worked for 1 out, and then you have to start imagining, well, if it worked for a string of length n, it'll work for one of n plus 1, and that in some sense, that testing it exhaustively right across all strings is of course impossible. So you have to kind of move to sort of a larger case where you can't just sit there and trace the whole thing. You'll have to, in some sense, take a faith thing that says, if it could have computed whether the interior is a palindrome, then adding 2 characters on the outside, right, and massaging that with that answer should produce the right thing. And so some bigger tests, right, that verify that the recursive case, right, when exercise does the right thing, then the pair together, right, all your code is going through, these same lines, right, the outer case going down to the recursive case, down to that base case, and that that's one of the beauty of writing it recursively, right, is that in some sense, once this piece of code works for some simple cases, the idea that extending it to larger cases, right, is almost I wouldn't say guarantee, that maybe makes it sound too easy, but in fact, right, if it works for cases of n and then n plus 1, then it will work for 100 and 101 and 6,000 and 6,001 and kind of all the way through all the numbers by induction. Oh, sure.
You'd have to remove all the all the space.
Yeah, so definitely like the was it a car, right, to mash, I definitely should be taking my spaces out of there to make it right. So you are totally correct about that. So let me show you one where recursion is going to definitely buy us some real efficiency and some real clarity in solving a search problem. I've got a vector. Let's say it's a vector of strings, vector of numbers, vector of anything, doesn't really matter. And I want to see if I can find a particular entry in it, right? So unlike the set, which can do a fast contains for you, right, in vector, right, if I haven't done anything special with it, then there's no guarantee about where to find something. And so if I want to say, well, did somebody score 75 on the exam? Well, then I'm going to have to just walk through the vector starting at slot 0, walk my way to the end, and compare to see if I find a 75. If I get to the end and I haven't found one, then I can say no. So that's what's called linear search. Linear kind of implies this kind of left to right sequential processing. And linear search has the property, right, that as the size of the input grows, right, the amount of time taken to search it kind of grows in proportion. So if you had a 1,000-member array and you doubled its size, you would expect that doing a linear search on it should take twice as long for an array that's twice as large. Okay. The strategy we're going to look at today is binary search, which is going to try to avoid this looking in every one of those boxes to find something. It's going to take a divide and conquer strategy, and it's going to require a sorted vector. So in order to do an efficient lookup, it helps if we've done some rearrangement of the data. In this case, right, putting it into sorted order is going to make it much easier for us to be able to find something in it because we have better information about where to look. So much faster. So we'll see that surely there was some cost to that, but typically binary search is going to be used when you have an array where you don't do a lot of changes to it, so that putting it into sorted order can be done once, and then from that point forward you can search it many times, getting the benefit of the work you did to put it in sorted order. If you plan to sort it just to search it, then in some sense all the time you spent sorting it would kind of count against you and unlikely to come out ahead. So the insight we're going to use is that if we have this in sorted order, right, and we're trying to search the whole thing, we're looking for, let's say, the number 75, is that if we just look at the middlemost element, so we have this idea that we're looking at the whole vector right now from the start to the end, and I look at the middle element and I say it's a 54, and I can say, well, if 75 is in this vector because it's in sorted order, it can't be anywhere over here. Right? If 54 is right there, everything to the left of 54 must be less than that. And 75 wouldn't be over there. So that means that I can just discard that half of the vector and from further consideration. And so now I have this half to continue looking at, which is the things that are to the right of 54 all the way to the end. I use the same strategy again. I say, well, if I'm searching a vector, so last time I was searching a vector that had 25 elements, now I've got one that's got just 12. Again, I use the same strategy. Look at the one in the middle. I say, oh, it's an 80. And then I say, well, the number I'm looking for is 75. It can't be to the right of the 80. It must be to the left of it. And then that lets me get rid of another quarter of the vector. If I keep doing this, right, I get rid of half, and then a quarter, and then an eighth, and then a 16th. That very quickly, right, I will narrow in on the position where if 75 is in this vector, it has to be, or I'll be able to conclude it wasn't there at all. That I kind of worked my way in, and I found a 74 over here and a 76 over there, then I'm done. And so that base case comes when I have such a small little vector there where my bounds have kind of crossed in such a way that I can say, wow, I never found what I was looking for. Okay, so let's walk through this bit of code that kind of puts into C++ the thing I just described here. I've got a vector. In this case, I'm using a vector that's containing strings. It could be ints, it could be anything, it doesn't really matter. I've got a start and a stop, which I identify the sub-portion of the vector that we're interested in. So the start is the first index to consider, the stop is the last index to consider. So the very first call to this will have start set to 0 and stop set to the vector's size -1. I compute the midpoint index, which is just the sum of the start and stop divided by 2. And then I compare the key that I'm looking for to the value at that index. So I'm looking right in the middle. If it happens to match, then I return that. So the goal of binary search in this case is to return the index of a matching element within the vector, or to return this not found -1 constant if it was unable to find any match anywhere. So when we do find it, at whatever level the recursion is, we just can immediately return that. Yeah, we're done, we found it, it's good. Otherwise, right, we're going to make this recursive call that looks at either the left half or the right half based on if key is less than the value we found at the midpoint, then the place we're searching still has the same start position, but is now capped by the element exactly to the left of the midpoint, and then the right one, the inversion of that, right, one to the right of the midpoint and the stop unchanged. So taking off half of the elements under consideration at each stage, eventually, right, I will get down to the simplest possible case. And the simplest possible case isn't that I have a one element vector and I found it or not. The really simple case is actually that I have 0 elements in my vector, that I just kept, moving in the upper and lower bound point until they crossed, which meant that I ran out of elements to check. And that happens when the start index is greater than the stop index. So the start and the stop, if they're equal to each other, mean that you have a one element vector left to search. But once you, if, for example, if you got to that case where you have that one element vector left to search, you'll look at that one, and if it matches, you'll be done. Otherwise, right, you'll end up either decrementing the stop to move past the start, or incrementing the start to move past the stop, and then that next iteration will hit this base case. It said, I looked at the last element in a one element vector, it didn't work out. I can tell you for sure it's not found. If it had been here, I would have seen it. And this is looking at just one element each recursive call. And the recursive calls, in this case, stack up to a depth, right, based on the logarithm of the size to the power 2. So that if you have 1,000 elements, right, that you look at one, and now you have a 500 element collection to look at again. You look at one, you have a 250 element, 125, 60, 30, 15. So at each stage, right, half of them remain for the further call, and the number of times you can do that, right, for 1,000 is the number of times you can divide 1,000 by 2, which is the log base 2 of that, which is roughly 10. So if you were looking at a 1,000-member array, if it's in sorted order, it takes you 10 comparisons to conclusively determine where an element is if it's in there, or that it doesn't exist in the array at all. If you take that 1,000-element array and you make it twice as big, so now I have a 2,000-member array, how much longer does it take? One more step. Just one, right? You look at one, and now you have a 1,000-member array. So however long it took you to do that 1,000-member array, it takes one additional comparison, kind of one stack frame on top of that to get its way down. So this means, actually, this is super efficient. That you can search, so for example, 1,000,000 is roughly 2 to the 20th power. So you have a 1,000,000 entry collection to search. It will take you 20 comparisons, right, to say for sure it's here or not, and here's where I found it, just 20. You go up to 2 million, takes 21, right? The very, very slow growing function, right? That logarithm function. So that tells you that this is going to be a very efficient way of searching a sorted array. It's a category of thing called the divide and conquer, right? That take a problem, divide it, and typically in half, but sometimes in thirds or some other way, and then kind of, in this case, it's particularly handy that we can throw away some part of the problem, so we divide and focus on just one part to solve the problem. Okay. All right, so this is the first one that's going to start to really inspire you for how recursion can help you solve problems that you might have no idea how to approach any other way than using a recursive formulation. So this is an exercise that comes out of the reader in chapter 4. And the context of it is you have n things. So maybe it's n people in a dorm, 60 people in a dorm. And you would like to choose k of them, and let's make k a real number 4, 4 people to go together with Flix. So of your 60 dorm mates, how many different ways could you pick a subset of size 4 that doesn't repeat any of the others? So you can pick the 2 people, from the first floor, 1 person from the middle floor, 1 person from the top floor, but then you can kind of shuffle it up. Well, what if you took all the people from the first floor, or these people from that room and whatnot? You can imagine there's a lot of kind of machinations, right, that can be present here. And counting them, it's not quite obvious. Unless you kind of go back to start working on your real math skills, how it is that you can write a formula for this. So what I'm going to give you is a recursive way of thinking about this problem. So I drew a set of the things we're looking at. So there are n things that we're trying to choose k out of. So right now I've got 12 or so people or items, whatever it is. What I'm going to do is I'm going to imagine just designating one totally at random, right? So pick Bob, right? Bob is one of the people in the dorm. I'm going to kind of separate him from everybody else mentally in my mind and draw this line and kind of mark him with a red flag that says, that's Bob. Okay. So Bob might go to Flix or might not go to Flix. Some of the subsets, right, for going to Flix will include Bob, and some will not. Okay. So what I'd like to think about is, how many different subsets can I make that include Bob? And how many different subsets can I make that don't include Bob? And if I added those together, then that should be the total number of subsets I can make from this collection. Okay, so the subsets that include Bob. So once I've committed to Bob being in the set, and let's say I'm trying to pick 4 members out of here, then I have Bob, then I have to figure out how many ways can I pick 3 people to accompany Bob to the flicks. And so I'm picking from a slightly smaller population, right? The population went down by 1, and the number I'm seeking went down by 1. And that tells me all the ways I can pick 3 people to go with Bob. The ones that don't include Bob, then Bob's just out of the running. I look at the remaining population, which is still 1 smaller, everybody but Bob, and I look for the ways I can still pick 4 people from there. So what I have here is trying to compute C of nk is trying to compute C of n minus 1 k minus 1 and add it to C of n minus 1 k. So this is picking friends to accompany Bob. This is picking people without Bob. Add those together, and I will have the total number of ways I can pick k things out of n. So very much relying on this recursive idea of, well, if I had the answer, I don't feel smart enough to know the answer, directly, but if I could defer it to someone who was actually willing to kind of do more, scrutiny into this thing, well, if you could tell me how many, groups of 3 you can join with Bob and how many groups of 4 you can pick without Bob, I can tell you what the total answer is. The simplest possible base case, right, we're going to work our way down to is when there are just no choices remaining at all. So if you look back at my things that are here, in both cases, right, the population is getting smaller. And in one of the recursive calls, right, the number of things I'm trying to pick is also getting smaller. So they're both making progress toward kind of shrinking those down to where there's kind of more and more constraints on what I have to choose. For example, on this one, as I keep shrinking the population by 1 and trying to get the same number of people, eventually I'll be stuck trying to pick 3 people out of 3. Right, where I'm trying to pick k of k remaining, where there's only one way to do that, which is to take everyone. On this one, I'll eventually keep picking people, so the k is always less than the n in this case, that the k will eventually kind of bottom out where I'll say, well, I've already picked all the people. I've already picked 4 people. I need to pick 0 more. And at that point, that's also very easy, right? Picking 0 out of a population, there's only one way to do that. So what we end up with is a very, very simple base case of if k equals 0, so I'm not trying to choose anymore, I've already committed all the slots, or if k is equal to n, where I've discarded a whole bunch of people and now I'm down to where I'm facing, okay, I got to get 4 and I've got 4 left. Well, there's only one way to do those things, and that's to take everybody or take nobody. And then otherwise, I make those 2 recursive calls with Bob, without Bob, add them together to get my whole result. That's wacky. I'm going to read you something, and then we'll call it a day. I brought a book with me. I stole this for my children.